Okay, so thanks very much. I'm Elisone from National Tsinghua University in Taiwan. And I'd like to thank the organizers for giving me the chance to share some of my work, even though I can't be there in person. And I'm going to spend the next quarter of an hour, hopefully slightly less, talking about cosmic rays as a feedback agent in primordial galactic ecosystems, and discuss the way they can modify the star formation histories of young galaxies in the early universe. So the results in this talk are based on these three papers, in particular this third one here. So if you want to know more details about the underlying models, the assumptions that have gone into them, the data sets we apply some of the work to, please do feel free to check these out. And I'll start off with my main claim for this talk, I suppose, which is that cosmic rays in primordial galactic ecosystems can deliver a powerful and progressive feedback effect. And this feedback effect can be powerful enough to even bring about the downfall of their star formation in the early universe. To set the context of this study, primordial galaxies are isolated, usually found in small associations, and their star formation is often sort of more bursty and more intense than that seen in the more local universe. So these high redshift starburst galaxies are rather different beasts to the starburst galaxies we see in the local universe. Their star formation is often thought to be driven by filamentary inflows of gas directly accreted from the cosmic web, rather than relying on interaction processes between neighboring galaxies. They're often isolated, they're not found in big cluster environments typically. And actually their star formation is often quite a lot higher than some of the galaxies seen in the nearby universe. So we can get an idea of this from the star formation density evolution over redshift. So we can see, probably familiar with this plot already, the cosmic noon at around redshift 2, and then at higher redshifts, the overall star formation rate density is lower, but the abundance of galaxies is much lower, which would point towards galaxies typically having, on average, a higher star formation rate. And observationally, there's indications of this, like star formation rates averaging a few hundred solar masses per year are not uncommon. And maximum star formation rates of a few thousand solar masses per year have been observed in some very high redshift galactic monsters. So this is kind of painting a picture of these galaxies being very vibrant in star forming activities, and also quite violent in terms of their energetics. So with all of this star forming activity, shortly after the onset of star formation, we should expect supernova events to start happening, and this would lead to the emergence of a population of supernova remnants inside these galaxies as well. So from this Hillis plot, which I'm sure you've seen plenty of times in the last few days, we get this idea that supernova remnants can accelerate cosmic rays to sort of PeV or tens of PeV in energy. And then these high energy cosmic rays can undergo hadronic interactions to inject leptons, electrons into the interstellar medium of their host environment. And this process will preferentially happen in regions of denser gas, which means that you're injecting these electrons, which then can thermalize relatively quickly in semi-ionized dense regions of gas, which is actually the site of subsequent star formation in these systems. So you can get this idea that there's a sort of a natural feedback mechanism that's arising here. So you have the star formation providing cosmic rays. The cosmic rays are targeting their interactions in these dense environments that are forming the next generation of stars. So if this process is powerful enough, maybe you can heat up that gas enough to a point where it can't collapse to form that next generation of stars anymore. So that's the general context and what might be going on in these environments. Now let's consider a case study. So the curious case of MAX 1149 JD1, like this came up quite clearly in the literature about 4 years ago in Hashimoto 2018. And this galaxy had been studied before as a lensed high redshift galaxy around redshift 9. And it was detected with ALMA, with O3, the forbidden O3 emission line, about 88 micrometers. And this O3 emission is quite a robust trace of star formation rate in these high redshift galaxies. So this detection allowed them firstly to get a clear determination of the redshift of the galaxy at about 9.11, and also a clear idea of what the star formation rate of the galaxy was. They found it was forming stars at a rate of about 5 solar masses per year, not too exceptional. Its redshift was more exceptional. It's one of the most distant star-forming galaxies ever detected. But what was even more interesting was actually when combined with the multi-wavelength data in the near-infrared and infrared band, spectral fitting models indicated in this earlier study that actually there was substantial evidence for, firstly, the young generation of stars associated with the ongoing star-forming activity, but also a much older red and dead population of stars. So this fitting was done just by evolving stellar populations, doing a Monte Carlo fitting process. And then they came up with an estimate for the age of the young stellar population, about 2 million years, associated with that ongoing star formation, and the old stellar population of age, on average, about 300 megayears, with some of the stars being about as old as 100 megayears at the observational epoch. So this was enough information for them to construct a star formation history. So the observational epoch at redshift 9.11 is here, where you have a star formation rate of about 5 solar masses. And then the older stellar population associated with the previous burst, based on the constraints they could get from the near-infrared SED, they could get a range of possible star formation histories, so ranging from very intense burst to relatively quiescent, about 10 solar masses per year. And the headline act of that previous study was that this pushed back star formation in the earlier universe to about redshift, potentially redshift 15, which of course is very startling, very exciting discovery. But for me, what I found was most interesting was this quiescent period here. Like, whatever star formation history you consider that's consistent with the infrared emission of this galaxy, you have to have a quenched period of about 100 megayears or 150 megayears, which begs the question, what causes the downfall of star formation in this galaxy? What brings this earlier burst to an end? So I applied a cosmic ray feedback model to this situation. So of course we have this sort of natural idea that cosmic rays are directing their heating effect into sort of more dense regions of gas. But in the Milky Way, we see that actually we need to contain the cosmic rays in that galaxy to some extent. So we can invoke a magnetic field development model based on turbulent dynamo amplifications, based on turbulence injected by supernova events. So this is not my own model. I just adopted a Schubert 2013 prescription for this. And this gave a magnetic field that amplifies relatively quickly, and does so more quickly in regions in galaxies that have higher star formation rates. And this would effectively stop the cosmic rays ballistically streaming out of the galaxy, practically contains them to a diffusion transport scenario inside the galaxy, and boosts their abundance by about 6 orders of magnitude or so. And this is important because this makes their heating power competitive with other possible means of feedback in this galaxy. So here, the gray lines are showing the case if you have like no containment of the cosmic rays, but if you contain those cosmic rays, the heating power becomes competitive with, say, more conventional means of feedback, so like radiative feedback from the stars, for example, or heating by X-rays emitted by hot gas. So with this heating power, we apply it to the star formation history models inferred by the Hashimoto 2018 study. So invoking the cosmic ray containment progressive heating model, like, so you build up the magnetic field to the saturation level, then this is sufficient to contain the cosmic rays, and they're delivering their full heating power after they've reached that saturation, after the magnetic field is saturated. So here this is and taking the initial values of the star formation, the onset of star formation from the previous plot, but not the final values. Here I calculate the growth of the magnetic field, the period in which cosmic ray heating reaches its full power, and then the time after this at which the gas reaches a temperature where star formation is practically stopped, like the gas is not able to undergo the gravitational collapse that's needed to form that next generation of stars, which we could argue would suggest that star formation should be quenched at that point. So you can see here, this plot looks remarkably similar to the previous plot, which is great. It suggests that cosmic rays could indeed do the job. Also, just as a side note, this kind of rules out the short burst of star forming activity as well. Like this full power of heating, cosmic ray heating, arises over a much shorter timescale than the dynamical timescale of the galaxy. So the galaxy can't really respond to that kind of heating. So we're suggesting sort of a more moderated heating effect. And this progressive cosmic ray heating does seem to be able to at least match the timescales that we're seeing to stop the star formation of the galaxy. And then for the gas to cool again through various mechanisms, it takes about another 100 megayears, 150 megayears to cool down to a level where the star formation can undergo a resurgence. So again, these timescales are conveniently quite similar to the ones that were inferred from the SED fitting. So this allows us to come up with a scenario where we can get a quenching time based on the cosmic ray heating power and a quiescent time period based on the amount of heating they deliver. And this provides us with a potential means to unravel feedback mechanisms in galaxies, in high redshift post-starburst galaxies more generally. But before I go on to that, we should discuss other possible means of feedback in these galaxies. So conventional means of feedback would be heating by starlight, for example, or AGN feedback. But in this case, I'm interested actually in galaxies that do not host an AGN. There's no evidence of an AGN, and we want to kind of understand what could be causing the stoppage of star formation if there's no AGN there. I mentioned before, starlight probably can't get into the regions that are most important for forming the next generation of stars, so we can practically rule that out as well, which just leaves things like violent mechanical feedback processes, perhaps mechanical energy injection from supernova or hypernova activity, which is in the literature still quite a popular means of delivering feedback in these primordial galaxies, or cosmic ray heating. So how do we distinguish between these two possibilities? Well, we can look at population studies actually. So if we have violent supernova activity, this is a stochastic process. Like after you reach a point where star formation is ongoing, there's no reason for a hypernova activity to happen at any preferred timescale after the onset of star formation, other than the evolutionary timescale of the star, which is relatively short compared to the evolution of the galaxy. So the quenching timescale should not really be related to the duration of the quiescence. Like the quenching can happen at any point, and then the strength of the quenching driven by the mechanical feedback would not be affected by the time at which that occurs. So this is a stochastic process. We should expect no correlation between these two timescales. If cosmic rays are doing the job, well, we have this progressive heating effect, and a heating effect where the timescale to bring about quenching in the galaxy should be inversely proportional to the duration of the quenched behavior. So if you're delivering more heating, it will quench the galaxy more quickly, and it will make the galaxy more quenched. So it takes longer for it to cool down to reinstate star formation at the end of that quenched epoch. So I decided to see what we could find in the literature using archival data, try and look at post-starburst galaxies that are selecting systems that do not harbor an AGN, have a relatively low star formation, but a high stellar mass, suggesting an earlier epoch of star formation. And see how these two timescales could compare, at least to the degree to which we could constrain their values in these systems. We found 11 possible targets, and the correlation looked like this. So we see a scenario, although there's large error bars and only a very small number of these post-starburst systems with sufficient information. A scenario where actually the quenching timescale is, if it's shorter, this would suggest a longer duration of quiescence. And if the quenching timescale takes longer to quench the galaxy, it stays quenched for a shorter amount of time. So this is all consistent with this, tends to be consistent with the progressive feedback process, and at least is in some tension with this sudden or stochastic process. So this is another point in favor of the cosmic ray scenario and delivering this progressive heating effect. But of course, no problem. But to really uncover whether it's cosmic rays doing the job, we need a much more robust determination of what this correlation truly looks like. We need to reduce these error bars. We need to get more data points onto this plot. So we have a requirement to pin down this progressive cosmic ray feedback in primordial galaxy populations. But conveniently, there's a lot of opportunity to do this, like with the new generation of facilities. So O3 emission with ALMA can reach very high redshift galaxies, determine their star formation rate at the observational epoch. And James Webb will allow us to get this very nice spectral data to get these star formation history models much more robustly constrained to determine whether it's a progressive heating effect happening or not. So that brings me to my final slide. So my key point here is that cosmic ray feedback should leave a distinctive progressive feedback effect in the SEDs of primordial galaxies, that we can access this information now, and we should be able to get good data on this in the coming years. And with broad population studies, we can really start to resolve feedback activity of cosmic rays in galaxies in early epochs of the universe, and try to understand their role in the structural evolution of the universe. So if you're interested to find out more, of course, feel free to ask questions. You can check out this paper as well to understand some more of the details that have gone into our model. But otherwise, thank you very much for your attention.